listening to you. Be careful about what you say.
Okay, so we will start our last keynote of today. I think we followed, I'm sure, by many discussions because you had many questions on the Google Doc related. So it is my pleasure to welcome Stéphane Mallat. So what is nice in Stéphane, when you have Stéphane Mallat, is that you don't need to ask him a biography. It's like inviting Joseph Fourier, because there is a Wikipedia page. So I think you all know Stéphane Mallat. So it's I read the Wikipedia page. It's one of the you know all Stéphane for being one of the main contributors of the development of the wavelet theory and its work. With Yves Meyer in multi-resolution analysis. I think today it will more focus on its main interest since the last year, which is scattering representation. So,
thank you very much. Thanks. I'm really very happy to be here because I think the topic is absolutely beautiful. The topic of Timbre is beautiful because nobody agrees about what really Timbre is. I read Wikipedia because, of course, it's the main reference to anything. And so I thought I knew what Timbre was, and then I checked in book, and each time I was looking in new book, I had a new definition of Timbre. So don't worry, I'm not going to try to give you my personal definition of Timbre. What I'm going to try to do is to approach the topic from a totally different angle, which is the angle of signal audio representation, and from a mathematical point of view to try to wonder what kind of property one would like to get out of audio signals in general if we want to do classification, if we want to analyze these signals. So it will be based on the work, very classical work of many people, but in particular also specific work of Vincent Lestanlen, who is here doing his PhD, and two ex-PhD students, Johan Brunat and Joachim Anven, who did part of the work. So I would like to look at the problem from the standpoint of classification. And once I can get out of the specific problem of audio, so here you have an audio signal. One of the specificity of audio signal, or one of the property of the audio signal, is that they are, as we all know, very high dimensions. So typically about 10 to the power 4 samples per second. And that is going to completely condition the major difficulty of the problem. So if you want to look at a classification problem, you all know what it is. So you have a set of examples, so different examples, for example, of audio signal xi. And a typical classification problem, you have a training example where you know the class of each example, yi, which is a function of xi. And what you want to learn is f of x. In other words, if you have a new example x, you would like to know what's the value of f of x. So f could be associating a word to an audio signal. It can be associating a label to an image, to a disease, to an electrocardiogram, whatever. And all these problems have a lot of things in common. And it's interesting to look at all these problems from a common point of view to try to see in what sense some of the audio problems are specific or not so specific. So one of the core questions first is, why are these problems so difficult? If you look at them from a little bit far away, it doesn't look so difficult, because after all, what you have is a set of example xi. You know the value of f of xi. You have a new f. You have a new sample x. You want to know what is the value of f of x. You just interpolate. You just pick the values xi that are close to x. You know the value of f of xi, and you just interpolate. Under what condition is that going to work? It's going to work if you have some example which are sufficiently close to the examples that you are now looking at, so xi which are close to x, and if f is regular. Now the reason why this absolutely doesn't work is that you have no example which are close to yourself. And that's not, of course, specific to audio. That's just a consequence of the fact that you are in very high dimension. So if you take a cube, 0, 1, let's say, to the power d, and if you want to sample this cube so that each of the samples are close enough, let's say to a distance epsilon, then obviously you will need epsilon to the power minus d examples or samples to cover your cube. So imagine epsilon is 1/10, so that you need 10 example to cover 0, 1. In dimension d, that will make 10 to the power d. If d is 100, 10 to the power 100, that's already the number of atoms in the universe, okay? And 100 is very small. An audio signal will be 10 to the power 4, so there's no way we can have examples which are close. That means that if you take an example x, there will be no xi which are close relatively to a Euclidean distance. So that's, of course, a big difficulty of audio signal processing, because if you, for example, take an accordion, so from a timbre point of view, you would say it's the same. But obviously, if you make a Euclidean distance between these two things, they are absolutely different. They have nothing to do with one another. If you take a cello and another piece of cello, same thing. I mean, obviously, the distance will be totally different. And these distances have no reasons why they should be smaller than these two distances. So that's the common problem of all problems in high dimension, whether it's audio signals, electrocardiogram, whatever you want. So you are in that situation. You have, imagine two classes, so the red and the blue points. Euclidean distances are absolutely non-informative. It tells you nothing whether there is no reason why a red point should be closer to another red point than a blue point. Okay. However, below this problem, there is some kind of similarity metrics. There is some kind of similarity metric which tells you, for example, in the case of timbre, that two sounds coming from, let's say, the same instrument have a certain type of similarity. Images of two different chairs have different type of similarities. Electrocardiogram of different diseases has a certain type of similarity, and so there is a notion of similarity, which of course is also dependent upon the task. And what's the dream of all learning algorithm is to be able to do a mapping from this x with some nonlinear function that are called here f of x, such that by miracle, in this new space, which may be of even much larger dimension, a simple Euclidean distance will give you an estimate of this similarity metric. Okay, so that's the dream, that you make a nonlinearity, and then you arrive, and a Euclidean distance basically will give you a metric which is equivalent to your similarity metrics that you are dreaming. And it's what all learning algorithm, the key problem of learning is finding this phi. Because once you have found this phi, it's very easy to classify. If you have two classes, because the points are going to get closer together because they are similar, a simple, for example, hyperplane will separate. So you can do linear classification, linear processing, everything will be easy as soon as you've been able to do that. So in some sense, we were speaking, someone was speaking about intelligence. For me, intelligence, this is what intelligence is. It's about understanding how you can do associations between things, how you can build up a distance which corresponds to the true distance of your problem. It's not about applying rules like it was thought at the time of expert system in the 70s or 80s. And if you look, for example, even problems which are based on rules, like, for example, languages, Google Translate doesn't work with grammar. It works with that kind of technique. It maps French in a Euclidean space, English in a Euclidean space, and then in the Euclidean space you looked at the distance. So that's a completely generic approach. Problem is how to define this phi. Okay, deep convolution network. As we know, deep neural network, it's an old story. There has been a revival, in particular with the work of Yann Lequin, which now is reaching very spectacular results through the work of many people. So what are these deep networks? Very strange. You begin with X, you apply a linear operator, which will be, for example, in time a convolution. And then you do a nonlinearity, an absolute value rectifier, whatever you want. And the output, we'll call that the output of a neuron, of an artificial neuron. And then you repeat. You reapply a linear operator like that, and then you reapply your nonlinearity. You cascade, you do that certain number of times. You're going to get a big array of number, which is now your representation phi of x. And now out of that, you apply a simple linear classifier, so just with your hyperplane. And the incredible thing is that you can get remarkable results. So what are the parameters in this problem? The parameters are these linear operators. And the number of parameters within this linear operator can reach 1 billion. And people are going to optimize these parameters so that the final classification is as good as possible. So it's not as simple as possible. There is an architecture, and there is a lot of prior information which is in fact put within this architecture, which constrains very much the problem. But what is spectacular is the fact that there are beautiful results in many, many different fields. Image processing, speech, music, biodata classification, and it's not just an academic world. I mean, major industries now are basing their products based on that. Facebook, IBM speech recognition, Google, voice on mail is based on that, Microsoft, Yahoo, and there are a lot of work from many researchers. Joan Bello, who is here, did a lot of work around that. The question is, why does it work so well? I mean, how come this bizarre cascade of linear operators and nonlinearities get you a phi of x which builds up the appropriate metric? And in what sense can this give us some information about this problem that we've been discussing, which is audio perception and timbre? So I'd like to organize the talk about a number of questions. So the central questions is, of course, how to build an audio signal representation so that you can use it for classification. What I mean by use it for classification means that then you just do a simple linear or Euclidean distance and linear operators, and you can classify. So how can one do that kind of thing? Why are deep networks appropriate for doing that? Wavelengths. I have a bias, of course, in this thing, but it's not just a bias. If you look, of course, and most of you know that, all of you know that, in the cochlea, there is something which is essentially a wavelet transform. In almost all classifiers that are being used nowadays, the first layers are wavelet transform. Why? Why does the wavelet transform come in? Is it an issue of compression? We don't care about compression. What's the problem? Why are there so many nonlinearities? So what I'd like to try to give to answer this question is to provide a kind of geometrical view of this problem of representation, and in particular, maybe of timbre. So geometry, I mean, it's bizarre to speak about geometry when you have a 1D signal. I mean, 1D signal, how much geometry can you do? It's pretty poor. So let's begin with time, okay? That's where we are. What can we say about time? If we think, for example, about timbre, you'll speak about the timbre of, for example, an instrument of a source. So that's typically something which is global, translation invariant. If you translate everything, is going to be the property is not going to change. So typically, if you have a signal which translates, you'd like to have a representation which doesn't change when the signal translates. Translation invariant. This is very easy to do. There is something which is in common in most of these problems, whether it's images, audio, and so on. If you take an audio signal and you do a very slight warping, you don't destroy your signal. You obtain something which is perceptually very similar. In the same way, you take an image, you slightly warp it, deform it, you have a similar image, and the distance is essentially given by the deformation. So stability to deformation. One claim is that this simple property is going to completely constrain the underlying mathematics and the kind of transform you can do. What does it mean for our transform? It means that once we are in the transform domain, the distance, Euclidean distance between the signal warp to the representation of the signal should be of the size of the deformation. And the size of the deformation is just the derivative of the warping. If the derivative of the warping is 0, it's just a translation, the distance is 0. Okay? So that's what we want to do. Now, this property, and of course, we want a representation which preserves enough information for doing the discrimination. Now, this simple property of deformation, as I said, is going to completely constrain the problem, and in fact, it's hard to get. If you think of translation invariance, the simple idea you can think of is the Fourier transform. Because if you take a signal, you compute the Fourier transform. Oh, here's it. If you compute the Fourier transform, if you translate your signal, you're just going to have a change of phase. So if you take the modulus, you now have something which is translation invariant. the representation of the translated signal or of the original signal is the same. What's the problem? Why nobody, almost nobody, uses Fourier transform for classification? Because it's unstable to deformation. In what sense? Take your signal and deform it a little bit. If you look at the Fourier transform of the deformed signal at high frequencies, it will be very different from the Fourier transform of the original signal at high frequency. Let me give you a very simple example. You have here a signal with several harmonics. This signal is just going to be a little bit deformed, dilated. So the low frequency harmonics just moves by a little bit. It's here, very small. However, when you move to higher frequencies, this is going to be amplified. And when you arrive by the fourth harmonics, the two don't overlap. So that if you make a Euclidean distance, they look as completely different, although from the ear point of view, they are extremely similar. What does that mean? That means that when you move to high frequency, you need to delocalize. You need to have something which is stable to deformation. And that's where wavelets comes in. As soon as you want something which is stable to deformation, mathematically you don't have the choice. You have to separate scales, and that's where wavelet comes in. The basic idea is that if you take a wavelet, you slightly deform it, it looks like the original wavelet. You take a sine wave, you slightly dilate it, it's a sine wave of different frequency, and it's orthogonal to itself. Okay, wavelets. So you have a wavelet function, psi of t, and what we're going to do is we're going to dilate it. Okay, so a wavelet is a bandpass filter over there, and when you dilate it in time, you are going to also dilate it in frequency, and you're going to get Q constant bandpass filter. The number of wavelets you're going to have within 1 octave is a parameter Q. So for audio, typically you'll get about 16 wavelets or 32 per octave. How do you choose Q? You'll have this notion of sparsity that is going to come in. So why sparsity is coming in all these problems? Because of course, intuitively, if you have a more sparse representation which creates many zeros, that means you are going to extract coefficients which concentrate most of the information. So we'll incorporate that. What is a wavelet transform? It's just, there is no orthogonality, nothing subtle here. It's just a bunch of filters with your different Q constant filter. And at the end, you will get the low frequencies that you haven't captured with all your bandpass filter. Okay, just a bunch of filters. And if you cover well your frequency axis, your wavelet operator is going to be preserving the norm. So there is no loss of information. It's just a series of bandpass filters. So we're doing here something very standard, but how are we going to get something which is invariant to translation? And that's the problem. If you take a signal X and you want a linear operator that gives you something invariant to translation, you don't have the choice. The only kind of linear operator you can use are just going to be time averaging. If you use a time averaging, so it's a convolution with a low-pass filter, a kernel, let's say a Gaussian, of size 2 to the j, you're going to get something much more regular, and this is going to be almost invariant to translation as long as your translation is small relatively to the size of your kernel. If you want to be fully invariant to translation, you let 2 to the j go to infinity, and you just get the average. And there we see the problem. The problem is that whenever we build an invariant, we are always very afraid of losing information. And here we've lost essentially everything. In the case of audio, you would just get 0. So where is the lost information? Well, the lost information, it's the high frequencies that you haven't captured. And we're going to capture them with wavelets because we want to be stable to deformation. Okay, so these are the wavelet coefficients. They oscillate with, let's say, the real and imaginary part. You have complex wavelet here. So we want to build something which is invariant to translation. If we just average that, you'll get 0. So we're going to do the same thing then with Fourier. You kill the phase. If you kill the phase, you get the envelope like that. And now you have something positive. So now, if you want something which is, okay, this is a little bit more invariant to translation because, of course, you've killed the oscillation. We all know that. But if X translates, the envelope is going to translate. So if you want really something which is invariant to translation, you need to average that. So if you average, Good, you're going to get something which is now much more stable to translation, but you've lost information. So where is the information that you've lost? In the high frequencies. How do you get the high frequencies? This was averaged. You are going to compute the wavelet transform of this quantity. And that's where we are getting to relatively standard audio tools and deep convolution network. So that's going to be the main slide. And it took me a long time to design it. So that's the signal x of t. We're in one dimension. First thing, you compute the wavelet transform, you get a standard scaleogram. Sometimes it's called spectrogram. That's why we never understand each other with Shihab. But that's basically a log frequency axis vertically, horizontally time, and you have about, let's say, 16 wavelet per octave. So you are now in 2D. And you took the modulus. Now, you want something which is invariant to translation, so you're going to average that in time. And you get now something which is much more blurred in time. And this is basically a Mel frequency spectrum representation. If the averaging in time is about 50 milliseconds, you get something like an MFC. But as I said, you've lost information. So what information you've lost? The high frequency that you lost by doing the averaging. So for each line there that you average, you're going to extract different frequency bands. That's my second wavelet, lambda 2. So I'm going to do a convolution with a second wavelet, psi lambda 2. So now I have three axes. Time, the original frequency, and now the second frequency of the second wavelet, which correspond to this notion of rates over there. So now you are in this 3D space. So now you can begin to think more about geometry. But these things are not invariant to translation. How do you make them invariant to translation? You average them in time. Good. You've averaged them in time, but you've lost high frequencies. So you need to get the third layer and so on. And what you see here is a convolution network, series of convolution, nonlinearities here modulus, convolution, nonlinearities, and so on. And in this case, these are the output of the network. The first layer is just the MFSC coefficient. These are, like we'll see, essentially modulation spectrum coefficients, and you can continue. So what we'll see is that this is very far from the end of the story. Oh, what if you average much more? Then you just get constant, and you have a completely time-invariant representation. Time essentially disappears because you are constant in time, and that's the modulation spectrum, completely constant. The time axis has completely disappeared. Good, so that's the representation. The representation is obtained from the original signal by cascading wavelet transform modulus, wavelet transform modulus, wavelet transform modulus, and so on. And you produce all these layers. First, the output of first layers for an audio signal is 0, second layer, third layers, and so on. Okay, that will be the only math results I'll be saying, but just to summarize the idea. Each operator WK preserves the norm. The norm of WKX is the norm of X. So if you take if you apply a modulus, you are going to get something which is going to contract, because applying the modulus is contracted. So these operators are contractive. If you cascade contractive operators, you get a contractive operator. So you know that it's going to reduce the distance, so you are stable. You can even show that the norm of the output is the norm of the input, so you preserve all the energy. All the energy of your signal will be transformed into invariant. But, much more important, you are stable to deformation. If you have a slight deformation, all this information is going to be stable and is just going to change by the amount of deformation, even if you just use a Euclidean distance. Okay, so how does it apply to audio models? So if you have an audio model which is an excitation pitched or random, filtered by a filter age with an amplitude modulation like that, one of the things you can easily verify, and that corresponds to these classical ideas of modulation spectrum, the second layer, which corresponds to modulation coefficient, essentially gives you information about the spectrum of the amplitude modulation. Okay? And I'm going to show that through example. This is the first example. You have 4 notes, different attacks, a tremolo, and a vibrato. That's the output of the first layer. Because you average the spectrum, all these components disappear. If you look at the second layer, you have the modulation spectrum. The attack was very small. So this second layer corresponds to the wavelet transform at this frequency for all lambda 2s. And so along lambda 2, there is no energy because, at high frequency because it was a smooth attack, sharp attack, the frequency of the tremolo, and the harmonics of the vibrato. So you see appearing within the second layer these structures. Now, if the excitation is random, it's the same thing. First layer, they all look the same. Second layer, you see appearing the specificity of the amplitude modulation. Third example, two signals which have exactly the same first layer, and the second layer is different. Why? Because there is some intermittency in the first one, so you see how the second layer is important to characterize it. Okay, so out of this kind of thing, you can do classifications. That was the work of Joachim Enden. I want to show that, in some sense, to explain, at least from my point of view, the limitation of classification point of view for looking at that. So this is a problem where you are doing classification of musical genre. You have different genres, each 10 classes, rock, classic, and so on. And you take your signal, you apply your preferred features, you apply a linear SVM, and you look at the result, how good the classification is. So the kind of results that you get is what you expect. If you use MFCC or delta MFCC, you get the same kind of result than if you just use the first layers because they are essentially the same. If you add up the second layer, which corresponds to second order coefficient, the error drops. If you add up, in this case, the third layer, doesn't change much thing. If you do a time frequency, and I will come back to that, and that's basically the cortical transform, it does improve a little bit, but in that case, not major. But the problem is that you get these figures, but it's very hard to understand why it doesn't work. Why didn't we go to 0? Is it because of the database? Is it because the representation and so on? You can see whether you are going in the right direction by choosing that representation, but the why it doesn't work is hard. To look at the why it doesn't work, it's interesting to look at analysis synthesis. So let me look at the problem which is be closer to timbre. Let's look at a stationary sound. Okay, so you can view that as a realization of a random process. Different example of marteau piqueur will give you different sound with same timbre. If you have a random process X and you apply this transform, because the transform is just doing convolution, it preserves stationarity, if it's stationary. Absolute value preserves stationarity. So all these things that you are having here, they are all stationary. Now, when you have something stationary and then you average, if you are ergodic, you are going to get an expected value, the average. You take numbers which are all stationary, you average them, it should converge to the expected value. So what you expect is that this is going to converge to a bunch of expected values. So now you can interpret this vector as just being a bunch of expected value characterizing an underlying process, okay? And the question is, are these expected values going to provide you the right information, for example, to characterize timbre or to characterize other type of properties that you may desire on your sound? So to look at this problem, we're going to look at it from the point of view of analysis synthesis, okay? And that's the work of Johan Brunas. So you have a signal X. You just know the output of your network of the first order and second order. Now, if you take 2 to the j be infinity, you are just going to know the averages, okay? There is time has disappeared. So the consequence of that is that the number of coefficients you are going to use is not so big. You can verify if the original signal is n samples, you are just going to get about log n first order coefficients, so few, because log n octaves, and log n squared for second order coefficient. So I'm going to show you the results based on McDermott and Simoncelli audio textures. So this is the original texture. This is the one we construct from the first order, which is essentially based on second order moments. And you see the spectrogram in the middle. And if you add up the second layer, you see if you add up the second layer, you basically get something close to rhythm. You get the intermittency phenomena. First layer, just Gaussian model, basically. Second layer. That's not so bad. We're here. Now, sorry, here. And the recon. And the last two. Basically, you and again. So you look at this example and it looks good. Basically, it looks like you've restored Timbre. Okay? So it looks good, you are very happy, but you are only looking at a very small part of the problem. You are looking at a very small part of the problem, and that's where the work of Vincent Lestanen begins. Let's look at that. It has a pitch, the pitch evolves. Not so good anymore. You capture the rhythm, but not extremely bad, but not so good.
I've been a Wikipedia editor since 2003, and I'm the founder of the...
No, pitch signal. Okay, you can say there is a prosody which is here, but you're far from capturing the voice or the timbre of the voice. Very long-range structures. Not great. Extremely bad. Okay, what's the problem? And that kind of problem, you don't see it so much when you get the classification. The problem is that we've been taking each channel and reprocessing each frequency channel independently one from the other. So there is no coherence between the information across channels because it was not encoded. So you need to incorporate this coherence across time frequency channels. Okay, let me 1 second go to images and then we'll come back to the work of Shihab. If you look at images, you need wavelets which are two-dimensional, okay? So typically for images, what you're going to do is you're going to take a Gaussian, and then your wavelet, you're going to turn it because you would like essentially to extract, let's say, edges in different directions. So this is the real part of your wavelet, imaginary part. That's when you do a rotation of the wavelet for different angles, and then you scale 2 to the j. So you have two parameters now in 2 dimensions. The scale associated to frequency, but also the rotation. Now, mathematically it's the same. Then you just do a convolution with the wavelet, you average, you get a wavelet transform, it conserves energy, and so on. The only difference is that now the wavelet has two parameters, an angle parameter and a frequency parameter. So how does it look, a deep network or a scattering transform like that for images? You take your image, you transform it at different scale, different edges, different orientation. That's the theta parameter. But now, the second wavelet transform, you are not just going to filter it spatially, you also need to filter it across angles. You need to use the fact that there is a very strong coherence across angle and to use that information. If you do that, I'm going to show you the equivalent of the audio problem. This is a texture. This is a texture reconstructed with a Gaussian process, and below reconstructed with the representation. So Gaussian works well. You have geometry, Gaussian absolutely doesn't work. That's what you get. You capture the geometry. Why? Because you've incorporated the interaction between angles. That's a third. That's from Johan Brunard. Of course. And you can see that through that, you are capturing very subtle geometry because you have all the interaction, not just of scale, but also of angles. And that's where comes the work of Shihab. So Shihab has been telling me for a long time, but I just couldn't understand why it was good. The idea of saying, well, you should look at that as an image, not just as a bunch of 1D signals, but as an image. And what I've been showing here is that he's absolutely right. You absolutely need to express the interaction between frequency, so therefore consider that as a time frequency image, and not just as a bunch of 1D signals. So the core idea of their work on Timbre with Daniel Pressmitzer and Mihaly Yanni, I think, was first you compute your wavelet transform, so your time frequency representation, and then you recompute a transform, but by considering that as an image. So you're going to build a 4-dimensional representation, not just 3D. Why? Because now you're going to filter jointly in time and in space. So you're going to have a wavelet which filters in time and in space. You make the product of these two things, you get a 2-dimensional wavelet. So you're going to convolve this wavelet with this 2-dimensional wavelet, but also with this one, this one, this one. You have one parameter which equals the rate, which is the frequency of the wavelet in time, and another frequency parameter corresponding to the frequencies of the frequency. In other words, the frequency line. So they applied that to do, and of course the beautiful aspect of his work is that they did neurophysiology of ferrets, and that's the work which has been going on for I think about 10 years, but he'll be able to tell you much more about that. And in the auditory cortex in A1, they observed that there were neurons whose impulse response looked like these separable wavelets I just showed you, which seems to indicate that indeed not only it makes sense mathematically, but it may indeed be, it looks like it's implemented in the visual cortex. So the work that they did with Daniel Pressmitzer and Shihab and so on is to try to use that for characterizing timbre. So the idea is that you have your 2-dimensional spectrogram, you apply your transform, you arrive in 4D. But for timbre, you are not interested in time invariance, and essentially not interested 5 minutes. So I need to accelerate. Give me 3 minutes more. And you are not interested in frequency. So you integrate in time frequency, and you go from 4D to these 2D pictures. And that's corresponding to piano, that's corresponding to violin. And what basically they show is that you can use that to discriminate. And they did classification with an SVM showing that it works well, that it's related to our audio perception, and there's a lot of psychophysics experiments. However, that's not the end of the story. And that's why I want to show where sometimes classification is not enough to understand the full problem. The thing is, why it's a bit strange. Look at this image. Vertically, this image is a bunch of Diracs. It's not a great idea to do a wavelet transform vertically, because you have a bunch of Diracs, very sparse. You do a wavelet transform, you dilute the information. So they are absolutely right about the fact that you need to have these frequency interact, but doing that is a bit brutal. Now, there are things which are very well known in harmony. If you take a vertical line, and let's say you have a single note, okay? How do you want to analyze that? That's the fundamental note. You want to enroll it into a spiral, okay? That's the second fundamental. If you enroll it in a spiral, which makes a whole tour for each octave, the second one is going to be aligned. The third one is going to go here because it's not a power of 2. The fourth one, because it's a power of 2, will go to the next octave. Fifth one goes here. Sixth one goes here, aligned with the third because there is a factor of 2, and so on. All this is very well known in dates to earlier or whatever. The fact that if you want to look at the geometry of harmonics, don't look at them vertically, look at them enrolled in a spiral. So what does that mean? That means if you do that, there is really 2 groups that you're going to get. All your frequency are going to be grouped in one group over there and another group over there. So you don't want to analyze it in these parameters. You want to analyze it in these parameters because when you apply a wavelet transform, you want to apply it on something that is going to be regular. So if you do that, again your signal, if you enroll it, that's what is going to be the time. So if you enroll this signal and you decompose it into a spiral like that, that's the first component here, second component and so on, you are going to get this image. You see this alignment and this alignment that corresponds to the first 2 groups. You take the next one, you get that, third one, fourth one. There are many notes in these, there are chords. What you see is that this is much more regular. It's much more regular, and now you can do your transform. You can do your transform Along what axis? This axis and this axis. So what does that mean? That means that the natural geometry, which is again very well known, is not just frequency, but it's the enrolled frequency. So you see appearing the angle theta of your spiral, which essentially corresponds, which is completely discrete, corresponds to the musical notes, do, re, mi, fa, sol, la, si, do, within a score. You see appearing your octave variable, which is just the octave here. And what you want to do, you want to do your transform in time, as you did, but along theta, which is a periodic variable, and along j. So you ended up in a domain which has 3 variables. Not because you care especially about music or whatever, just because you look at the geometry and you want to sparsify your signal when you're going to apply your transform, otherwise you're going to lose the information. This is Shepard tone of Ricet. Okay, here's the so you see, if you do your transform vertically, it's going to be a nightmare. You have plenty of Diracs, you are going to completely dilute the information. If you represent this information within this 3D space, that's how it looks like. You see this spread over there. This spread encodes the slight slope over there. The fact that it's not horizontal, but it has a slope, so it encodes the frequency variability of the pitch, okay? And then the fact that it moves, you see it moving here. So once you have that, you do a transform of that. What do you get vertically? What you get vertically is the response of the transfer function of h. So what are you doing? You are separating A, the excitation and its modification of the pitch, and the h. So when you do that kind of transform, then you arrive in a 5-dimensional space. So the geometry is getting more complex. It's going more complex, but the analysis of the coefficient is much simpler. Because when you look at the variation of this coefficient relatively to this variable, which was the rate, we've seen, you just get essentially the amplitude modulation. If you look at the variability of this coefficient relatively to, let's say, the musical notes, the chroma, you will get something which just depends upon the pitch variation. If you look at the variability with respect to the octave, you get something which characterizes the envelope of the resonator. So that shows why you need to explode the thing. So whether you do a reconstruction, which is much better, Vincent will come back here in 1 year to show you that, but in the meantime, we'll see. Okay, I'd like just to finish with remarks and questions. So the first remark is that I think that the point of view of classification is very useful because, after all, what we want is a representation which captures the information. But again, the analysis synthesis point of view, I think, is also very important to try to really capture what has lost. So one problem which I'm very fascinated with is the relation between image and audio perception. That's a very well-known problem, and there's this beautiful book by Bregman, Auditory Scene Analysis, which shows there is a lot of things from a perceptual point of view which shows the similarity. The claim is that mathematically also the problems are incredibly similar. They are incredibly similar because they have the same property, the same stability to warping. The day you apply your wavelet transform, you arrive in spaces where you have the same problem. The variables that comes in are similar. You see appearing angle variables, scale variables, and so on. And so one of the questions is, could we translate audio into images and reverse? I don't know, but that's, I think, a very nice problem. That's not just about doing visual illustration of audio, but can you take an audio signal, transform it into an image, then which makes sense, relatively, and then come back in the same way you translate French in English and reverse? I think it should be possible. Well, Timbre. So obviously you've seen I don't know much about Timbre besides general culture and listening to you, but I do have a tendency to believe that Timbre comes from a consequence of something else, and from a consequence of something else, which is the property of audio signals. Audio signals come from the physical environment, have certain property, harmonicity, you have time, you have warping, and so on. And what I was trying to show today is that this implies a huge amount of constraints on the way you want to do your representation. You essentially don't have the choice. don't have the choice because you need wavelets to have your stability. And then if you want to adapt yourself to the harmonicity properties and so on, your hands are tight. So it could be that we can just unroll these mathematical property and arrive something which is close to Timbre. One of the fascinating problems for classification, and I think for everybody, is of course large-scale structures. Until now, all the research has essentially concentrated on 50 milliseconds, 100 or 1 second. What about capturing things like 10 seconds or even more? Musical phrase. Is that possible? And to do that kind of thing, I suspect your space will become more and more and more complex. We've seen how we went from 1D to 2D to 3D and in 5 dimension, and probably even more, which just is a way to express interaction with a different component. Last question I have, deep networks. So all what I did here has a deep network structure, but none of the filters that I showed here are learned, because they are all produced as a consequence of the physics of the problem. Right now, deep networks are learning, and I suspect that these learning algorithms are, in fact, recovering that kind of filters. So one of the questions will be, at the end of the day, is it necessary to learn these deep network filters, or will we be able to know what are the filters just as a consequence of geometry? I have a tendency to believe that it will be the case. Of course, you have final classification at the end using SVM because it depends upon the specific property of a sound. But I have a tendency to believe that this beautiful work that is now being done on this deep network filter is just opening the problem. And it's now a little bit up to us to try to understand why and potentially be able to analytically derive all these filters. So that's
okay, thank you very much, Stéphane. We have plenty of time for questions, so you can ask a question to Stéphane, and also Shiab Shama is online with us via Skype, so he can join the discussion and you can ask questions to him. And actually, I think it's also interesting because Stéphane asked questions, such as the last one. I was looking at one during he was telling that. So if you don't have questions, I can animate it. But
yes.
Emmanuel. Thanks for the great talk. I was wondering about the representations that you presented. So it seems that they support deformation across log frequency or scale, as you might define it, and they also support invariance to translation. What I'm wondering is if these representations can be affected by deformation across time. So if you have, let's say, a piece with a different tempo stretched across time, does that affect your classification?
So what I'm basically showing is that it's going to linearize the deformation across time. So if the once you linearize the phenomena, if the deformation across time is important because your goal is to measure whether there is a deformation or not, the SVM will preserve it. If you don't care, when you have a linear phenomena with a simple linear projector, you kill it and you build an invariant. So in some sense, you can view this nonlinear transform as a preparation to linearize the phenomena that you are potentially interested in. And then the final classifier is there to say, for this particular task, I can get rid of this, and this, and I'm only interested in that. And time warping is taken care of. Frequency warping is taken care of because of the wavelet transform along frequency that was proposed by Shihab. And then the other properties, we need to understand what we need, really.
What about non-stationarity? Because most of the examples you show are...
Well, the piano and so on are highly non-stationary. So here is complicated. If you want to get something which is... it's complicated to understand what is non-stationary in this framework. Because if you like a melody, okay, you can reconstruct a melody from completely delocalized coefficient. I'm not showing here, but for example, the melody in images would be the equivalent of shapes. You can reconstruct shapes from completely delocalized coefficient if you have enough coefficients. So and I'm still very confused about this notion. When you have something which is completely ergodic and the time average gets you the expected value, then you need much fewer coefficients, but you will never restore exactly the same thing. If you have something very sparse, like a simple melody, a simple shape, with this coefficient you reconstruct it. At least on images we know how to do that. So, as I say, you see in these problems, and I'm going to take the case of images, you want to have your feet on both ends. If the image is a shape, geometrical shape, you want to characterize it. If the image is a texture, you want to characterize it, but you are not interested in the details. You want a representation, and it's the same for audio. You want to be able to follow perfectly harmonic line, but if you have an audio texture like ta-ta-ta-ta-ta-ta-ta, you are not interested in all the detail. There's too much for you to absorb. You want to get both ends. And my impression is that kind of transform has the ability to do that. And that's what we're trying to show through analysis synthesis.
Non-harmonic sounds?
Non-harmonic sounds probably. I mean, if it doesn't follow the geometry, it's going to, probably the reconstruction is not going to be good. In the same way that you saw, we have very bad reconstructions of pitch signals if you don't incorporate the pitch geometry in the transform. So they are going to be harder to reconstruct.
I was wondering if in this framework, if it's possible to control the extent of the shift invariance in these kind of things. For example, when I think of, for example, in Timbre, the position of performance is very important. So the absolute position of performance is important. So a little bit of invariance is good, but too much would be not so good, I assume.
Okay, so for example, in all what we did here, we didn't average in frequency.